In this video, we'll be talking about quadratic equations. This particular quadratic equation, 3x squared minus 9x, is a quadratic specifically because it has x squared somewhere in the equation. Now, it's also important to note that if this had an x cubed in it, this would not be a quadratic but would be a cubic. So it's important to note that a quadratic equation must have x squared in it, and x squared must be the largest power of x that occurs in this entire equation. Now, with that defined, we're going to look at the three possible ways we could solve a quadratic. The first method is factoring. Factoring is a necessary skill in this course. If we're not terribly comfortable with it, we're going to have to make sure we practice it more. We will go through at least 2 or 3 examples of factoring. The second example is square root property. Now, the square root property is a very special case, and it only works in very special circumstances. Now, however, we could utilize complete the square, which will be in a separate video, to get every single quadratic equation into the form that we could use the square root property. And thirdly, the quadratic formula. Please avoid using the quadratic formula in every single case, even though the quadratic formula will satisfy every single case. I believe that this particular formula actually causes more work when you avoid factoring, because the factoring skill is absolutely necessary. So in this first example, looking at it, I can identify that there is what we call a greatest common factor. Again, GCF. The fact that I noticed that, and again, notice the first method that we have available is factoring. So I'm going to check factoring before I check anything else. So when I go to factor this, you'll notice that again, there's a 3x squared minus 9x. There is an x in both of these two terms. Now keep in mind, I'm treating the equal sign as a separator. I am never going to solve a quadratic equation unless it is first equal to 0. Once it's equal to 0, then I may attempt to factor, or square root property, or quadratic formula. Now in terms of factoring, all the terms together, when it's equal to 0, must have something in common for a GCF. If they don't have anything in common for the GCF, then GCF is not the factoring method that I will utilize. So in this example right here, I'll notice that I can divide this first term by a 3 and the second term by a 3. I'll also notice that I can divide the first term by an x and the second term by an x. And this is, again, something conceptually that I'm going to show, but I'm not going to divide the other side by 3x. Because, again, dividing the other side by 3x removes the 3x from the entire existence, and it actually causes us to lose information. I'm going to show you that the division of 3x works, just so you can help yourself simplify this down. So my greatest common factor is 3x. That is one of the factors that's going to be left. When I simplify the 3 divided by 3 and the x squared divided by x, I'm going to be left with an x in that term. I'm going to carry down the minus sign. The 9 is going to simplify with the 3, giving me a 3 left over, and x is going to cancel out with x, giving me 3. And this is all still equal to 0. Now, there's something called the zero factor property, which is a times b equals to 0. If a times b equals to 0, and let's just say, for instance, b is 5. If b is 5, the only number that a could be is 0. So that means 0 times 5 must be 0. However, what if I said that a was 5? Well, that means that b must be 0. Again, the only numbers that multiply together to get 0 is 0 and another number, which means that when I'm looking at this set of factors, 3x technically behaves like a, and the x minus 3 separately behaves like b. So my two options are 3x equals to 0 or x minus 3 equals to 0. Again, either a had to be equal to 0 or b had to be equal to 0. It could be both, but it has to be at least one. So in this case, I'm going to check both possible cases. If 3x equals to 0, I'll divide both sides by 3. And now, the difference between 0 divided by 3 and 3 divided by 0 is that I have, say, 0 pizza, and I'm dividing it between 3 people. No one gets any pizza. So x equals to 0. Over here, I'm simply going to solve this as though it's a linear equation and add the 3 to both sides, giving me x equals 3. And if you were to take these numbers and plug them back into the original equation, again, keeping in mind that the original equation was 3x squared minus 9x equals to 0, plugging in 0 gives me 0 minus 0 equals to 0, check. And plugging in 3 gives me 3 times 3 squared, which is 3 times 9, 27, minus 9 times 3, 27, and I get back 0. Both of those values check. Now, that is one method of factoring that we could use. A second method of factoring, if we're looking at this type of equation, must be utilized differently. Now, keep in mind, If you try to attempt a GCF on this side, your zero factor property, which I'm going to write that down, your zero factor property does not apply. It only applies when the factors multiplied together equal to 0. So it equaling to 1 fails to utilize that property effectively. So anytime that I go to solve a quadratic equation, my first step is getting it equal to 0. Again, I'm going to subtract the 1 from both sides to ensure that my quadratic is all on one side and 0 is on the other. Next thing I'm going to do is I'm going to use a method of factoring that I like to call rainbow. The only reason I like to call it rainbow is because it's taking this 2 right here and this one negative right here, and it's multiplying them together, creating what, again, looks like some semblance of a rainbow. Now, you could attempt to use guess and check to factor this, but this is a little bit more sufficient and more complete. So, I'm going to take 2 and I'm going to multiply it by a negative 1. I'm going to ignore the x squared, but it is the x squared term that gets multiplied by the constant term. That's going to provide me with a negative 2. I need to multiply to get a negative 2, but I need to add in order to get a 1. Now keep in mind, this 1 right here is coming from the in front of x. So again, it's the a and c value. Let me rewrite this down. Ax squared plus bx plus c equals to 0. That's your first step. You're going to have a times c over here. We want to multiply to get that, and you want to add to get your b value. This is the setup for factoring using what, again, I like to call rainbow. So what are the factors of negative 2? Well, 1 and 2 work, but one of those numbers has to be negative. So I'm going to make the 1 negative for a second. And then my completionary tells me that I'm going to simply go ahead and do 2 and 1, where I make the 2 negative this time. You'll notice that when I add negative 1 and 2 together, again, when I add them together, I get a positive 1 here, and I get a negative 1 here. So this is the pair of numbers that actually works to make that middle number 1. Now, to factor this is the part where things get a little bit hectic. I'm going to carry down the first term and the last term unchanged. In the middle, this plus 1x, I'm going to tear that plus 1x into 2 terms. I'm going to turn it into these 2 terms right here. But since there's an x here, those 2 terms must have x plus 2x. Notice the sign is also important. The negative 1 is going to be in front of the negative, and the positive 2 is going to still have positive 2. Now with these 4 terms, I can use a method of factoring called grouping. I'm going to group these 2 terms in front here together, and I'm going to group these 2 terms at the back end together. And out of these 2 terms, I'm going to use, again, GCF factoring. So what can I factor out of, again, both of those terms together? So over here, what I'm going to factor out of both those terms together? And the answer is I'm going to factor out an x, leaving with 2 times x, because there was x squared, there's 1x left, minus 1. Over here, I can't factor anything out. There's nothing in common. But if there's nothing in common, that means I can factor out a positive 1 always. I could factor out a negative 1, but that would change the signs. Now you'll notice here, I have x times this parenthesis set here, plus 1 times this parenthesis set here. For this method of factoring to work, those 2 pieces inside the parentheses must be exactly the same. That is one of your factors. Secondly, whatever's left over outside is your other factor. So x plus 1 in a set of parentheses is your other factor. Keep in mind, I ignored this equal to 0. I'm going to carry it all the way down here because it doesn't affect any of this factoring stuff in the middle. This is a process that we utilize to get those 2 factors. And now, once it's equal to 0, 2x minus 1 equals to 0, or by the 0 factor property, x plus 1 equals to 0, in which case x equals, I'm going to add the 1 and then divide by 2, 1/2. And here I'm going to subtract the 1, giving me x equals to negative 1. And again, we should take these values and we should plug them back in to the original equation to check. I'm going to bypass that step and identify the fact that they will both check. This provides us with the methods of GCF factoring, or this method here, which again I like to call rainbow. It's really just a method of factoring any trinomial factor. Now, after we've done those 2 methods, our next method will be using the square root property. The square root property specifically affects questions that do not have an x term. Now when I say x term, I don't mean an x squared at all. I don't mean an x at all. I mean a singular x power. That term is not existent in the equation. And again, this is the square root property. So when I'm looking at this equation, Again, we could attempt to try and factor this, but it would be unnecessary other than factoring out a 3 for both of those terms. What I'm going to do instead is I'm going to note that x squared is the only variable I'm looking for. I'm going to try and get x squared all by itself. You'll notice since there's no other x's in this problem, I don't have to worry about having to do anything else other than getting x squared by itself. So I'm going to add 21 to both sides, getting 3x squared equals to 21. I'm going to divide both sides by 3, getting x squared is equal to 7. And my next statement is, what value can I plug in for x that will give me 7 when I square it? Well, the number's not nice, but if I gave you an equation, say x squared equals to 4, then you could tell me that x could equal to a positive 2. But you could also tell me that x was equal to a negative 2. Now, if you don't trust me, again, the idea is you're replacing the x with that 2, and you're replacing the x with that negative 2. If you were to accurately plug in the negative 2 into this equation and replace that x with a negative 2 in parentheses, squaring that negative 2 is the same thing as negative 2 times negative 2, giving me a positive 4. So both of those values should check in here. Now what's important to note is that both of those values are also equivalent to nothing more than the square root of 4. So when I add two numbers to both sides, I'm simply canceling out a negative. When I'm dividing both sides by a value, I'm simply canceling out a multiplication. When I want to eliminate just a square root, when I'm eliminate just a square, I must square root both sides. But I must account for the fact that there could be a positive case and there could be a negative case. Because again, plugging in 2 to this equation will work. Plugging in negative 2 to this equation will also work. So every time you take the square root, you must put a plus or minus on that problem. The last example in terms of the square root property is nothing more than x plus 5 quantity squared equals to 11. Now, this also appears as though it does have an x term in it. But if in reality you look at it very carefully, this entire thing is something squared. There's no x's outside that something squared, which means that I can treat this like it's a square root property. If I have something squared equals to just a number, I may take the square root of both sides immediately, not forgetting to add the plus or minus in front of the numerical side. Something squared inside of a square root simply cancels out and leaves me with what's left inside. And again, it's very important to note that the square root and the square cancel out. This x plus 5 doesn't cancel out. It is still there. And it is equal to plus or minus the square root of 11. Then I will subtract the 5 from both sides, and again, I can't combine a negative 5 with a radical. So all I can do is rewrite that negative 5 in front of that radical. Again, since there's no radical on the 5, there's no combining these two terms. It's also important to note that there are then two solutions to this. Negative 5 plus radical 11, and x equals negative 5 minus radical 11. These are two separate solutions. It is important to note that the plus or minus is simply a placeholder for two possible cases. Now this is the square root property. There's going to be an additional video on complete the square separate from this. That complete the square method again is to allow you to get it into this form or this form, such that you have something squared and no linear x term.